Welcome back to the Deep Dive. If you're tracking the absolute frontier of AI, the biggest challenge right now isn't just training bigger models. It's about how to make them smarter without, completely breaking the bank. Today, we're plunging into a research stack that details a really radical answer to that problem. It's a new approach to scaling called conditional memory, and it's implemented with this module they call Engram. Our mission for you is to understand not just what this is, but how it solves a fundamental sort of hidden inefficiency in these huge models, like mixture of experts. And critically, why fixing this one thing seems to unlock these massive, unexpected gains in reasoning and even in code performance. Okay, so let's set the stage. We talk about intelligence in LLMs all the time, but if you really break it down, it's two totally different jobs, right? You've got the deep dynamic computation, that's the reasoning, the logic, and then you have the simple static knowledge recall, just remembering facts.
And that's exactly where let's call it a design flaw of the original transformer architecture really shows itself. A transformer doesn't have a memory button. It has no native way to just look something up. So when it needs a static fact, it's forced to use its entire computational stack, all those attention heads and networks, to basically simulate retrieval through computation.
So it's solving a simple lookup problem with a really complex, slow, sequential math equation.
Precisely. Imagine trying to remember the capital of France, but instead of just accessing that fact, you have to run a series of logical proofs through 7 layers of your brain to land on Paris. It's a profound waste of the model's most precious resource, its sequential depth.
And inefficiency, as we know, is the absolute enemy when you're trying to scale these things up. The gold standard right now is mixture of experts, or MoE.
Yeah.
We use it for conditional computation. It means we can have these models with trillions of parameters, but we only fire up a few experts for any given token. It keeps the compute costs, the FLOPs, manageable.
Right. MoE's is brilliant for dynamic tasks, deciding how to structure a sentence, solving a logic puzzle. But it still uses that expensive computational depth for simple retrieval. And the sources we have gave this fascinating data from a tool called patch scopes, which lets you see what each layer is actually doing. They track a really simple task, resolving the entity, Diana, Princess of Wales.
When I first read this part, I was just shocked at the wasted effort. I mean, this is basic knowledge. And the model spends half a dozen layers just figuring out who she is.
It's the perfect illustration of this inefficiency. Let's just walk through it. So the first few tokens hit the model. Layers 1 and 2 are just busy figuring out the word Wales. They're basically confirming, okay, this is a country in the United Kingdom. Then layer 3 refines it a bit. Okay, country in Europe.
Right, so we're 3 layers in, and we haven't even gotten to the person yet.
Exactly. Layers 4 and 5 are still wrestling with the title Princess of Wales, just trying to figure out the general context. It's all very unspecific. It's not until layer 6, that the model finally collapses all that work and resolves the full entity. Diana, Princess of Wales.
So in a 30-layer model, you've just burned 20% of your entire network's thinking time on what is essentially a glorified memory lookup.
And that has a real cognitive cost. That's capacity that should have been used for higher-level reasoning. This is the problem that drove them to look for what they call a complementary axis of sparsity, conditional memory.
So the answer is to build a proper memory architecture. And that's where Engram comes in. It's the module that makes this idea of conditional memory a reality, basically modernizing the old idea of engrams to allow for instant, constant time lookups. And when we say constant time, we're talking about O1 complexity, which means no matter how huge this memory gets, 1,000,000 facts, 1,000,000,000,000 facts, the lookup time doesn't change. It's a single quick request instead of a 6-layer calculation. But, I mean, O1 at that kind of scale sounds like an engineering nightmare.
Oh, it absolutely is. And that's why the architecture is so clever. They had to solve for density, speed, and maybe most importantly, noise. And they did it with 3 key innovations. The first is something called tokenizer compression. Standard tokenizers often give different IDs to words that are semantically the same, like apple with a capital A versus apple with a space before it.
So they're the same concept, but they're taking up 2 different slots in the memory.
Exactly. Engram uses a projection layer to collapse these into one single identifier. That alone reduced the effective vocabulary size by about 23%.
That's fantastic. Just low-hanging fruit right off the bat. So what's the next challenge? Getting the data out fast.
Right, the retrieval itself. For speed, they use multi-head hashing. It maps the context, the engrams, to a specific spot in this giant embedding table. Hashing is super fast, but with a huge table, you're going to get collisions. One context accidentally points to a memory slot with something totally irrelevant.
And if you're pulling up irrelevant data, you're just injecting noise straight into the model's brain.
Yeah.
How do you stop the memory from derailing the whole process?
And this is the third and most critical piece, the context-aware gating. This is the conditional part. The model's current hidden state, what it's actively thinking about, acts as a query against the memory that Enneagram just retrieved. The model is basically asking itself, okay, I just found this fact. Does it actually fit with what I'm trying to do right now?
So the gate isn't just a door, it's a security checkpoint. It's checking the memory against the current context.
Exactly. It dynamically modulates how that memory gets fused in. If the retrieved fact conflicts with the context, maybe from a hash collision or something, the gate just suppresses it. It ensures semantic alignment.
And it makes perfect sense where they put it. The sources say they did tests and found that putting it in early, at layer 2 specifically, was optimal. You offload that memory work before the big, expensive transformer layers even get started.
So with this new tool in the toolbox, the researchers faced this central question of resource allocation, the sparsity allocation problem. If you, the listener, have a fixed budget of, say, 27 billion sparse parameters, how do you split it? Do you put it all into MOE experts for computation? Or do you shift some of that into Enneagram memory?
My first thought, just my gut instinct, would be to stick with the experts. More MOE capacity should mean better reasoning, or why would taking experts away help?
That's the logical assumption. You'd think it would just be a straight line, more MOE, better results. But the evidence just shattered that idea. They found this incredibly consistent and robust U-shaped relationship between the validation loss and how they allocated those parameters. A pure MOE model with 100% of the budget going to experts was always suboptimal.
A U-shape. So if you're too heavy on MOE, you're wasting all that computation on lookups like we just talked about. And if you're too heavy on Enneagram, I'm guessing you just don't have enough horsepower left for actual reasoning.
That's the perfect way to frame it. The U-shape proves you need both. And they found the sweet spot. The optimal allocation was taking about 20 to 25% of that parameter budget away from MOE and putting it into the Enneagram memory layer.
Okay, and this is where the data gets really wild. They compare the models to the Enneagram 27B against the pure MOE 27B. The Enneagram hybrid was better across the board. Now, you'd expect the biggest jump on knowledge tasks, like MMLU, because that's what the memory is for, and it did improve by a solid 3 points.
But, and this was the huge surprise, the performance gains were significantly larger in complex reasoning, in math, and in coding. The very tasks that are supposed to be all about computation.
Wait, you're telling me that adding a better memory made the model better at thinking?
It did, exactly. BBH, the big general reasoning benchmark, improved by a massive 5 points. ARC Challenge, which is complex scientific reasoning, went up by 3.7. And HumanEval, for coding, jumped by 3.0 points. It strongly suggests that by taking the retrieval burden away, the MOE experts that are left are just way more effective at their actual job, high-level computation.
That synergy, memory-boosting reasoning, it really backs up their core idea. Enneagram isn't just adding memory, it's acting like a depth multiplier for the whole network.
And they have some incredibly specific evidence for this. They used a technique called logit lens analysis. Put simply, it shows how quickly a layer starts making good predictions. The Enneagram models showed a systematically smaller KL divergence in the early layers.
Meaning the model gets to a stable, confident prediction much, much faster in the Enneagram architecture?
Correct. And then they back this up with CKA analysis-centered kernel alignment. It's a technical way of measuring how similar the activation patterns are between different layers.
Okay, so CKA is like a structural fingerprint test for the layers.
That's a great way to put it, yes. And the fingerprint test showed this massive functional alignment shift. The fifth layer of the Enneagram model was structurally and functionally doing the same job as the 12th layer of the MOE model.
Layer 5 is the new layer 12. That's direct proof of the depth multiplier. By outsourcing memory, the main network can do much deeper work much earlier.
And this has huge implications for long context. The attention mechanism is supposed to handle global context, but if it's busy trying to remember local things, like who's who in a long document, it eats up all its bandwidth. By giving those local tasks to Enneagram, you free up attention to focus entirely on the global picture, on dependencies across thousands of tokens.
The attention system can finally see the forest instead of getting lost counting the trees. What did that do for performance?
A huge jump. On the needle in a haystack test from the ruler benchmark, the MOE model got 84.2% accuracy. The Engram model jumped to a near-perfect 97.0%. It's just dramatically better at connecting distant facts because its resources aren't being wasted on local trivia.
So far, we've covered the architectural gains, the cognitive gains, but Engram is also this fundamental breakthrough for infrastructure, for dealing with the headache of GPU memory limits.
This is one of the most exciting parts if you're on the operational side of things. MOE relies on dynamic routing. The next step depends on the current hidden state, which means you need those experts on expensive, high-bandwidth GPU memory, HBM.
Right, which is why we're limited by the few hundred gigabytes you can stick on a GPU.
Exactly. Engram, though, uses what they call deterministic addressing. The memory it needs to fetch depends only on the input tokens, not the changing internal state.
So because you know ahead of time what memory you're going to need, you can prefetch it?
That is the core innovation, the prefetch and overlap strategy. While the GPU is busy computing one block, the system is already pulling the Engram embeddings for the next block. And here's the kicker. It's pulling them not from scarce GPU memory, but from the abundant, slower host memory, the DRAM over PCIe.
So you overlap the slow data transfer with the computation that was going to happen anyway, effectively hiding the latency. The GPU is doing its homework while its assistant is already getting the next set of books.
And the result of this hardware-software co-design is just revolutionary for scale. They tested this by offloading a massive 100 billion parameter Engram layer entirely to host memory.
100 billion parameters.
Yeah.
Sitting on the computer's regular RAM, not the GPU. What was the performance hit?
It was negligible, a throughput penalty of less than 3%.
Less than 3%.
Less than 3%. This basically bypasses the GPU memory wall for factual knowledge. It proves you can just keep adding memory, keep driving down your validation loss in what they call the infinite memory regime without increasing your compute cost.
That is a staggering result. We're no longer limited by how much HBM we can cram onto a GPU. We're limited by a machine's DRAM, which is orders of magnitude cheaper and bigger. It completely changes the game. Wow, this has been a deeply satisfying exploration. If we boil it all down, the big takeaways really center on complementarity. First, combining conditional computation from MOE with conditional memory from Engram, specifically in that 7-5-25 split, is just flat out superior to trying to make one tool do every job.
And second, that this combination doesn't just add a feature, it fundamentally changes how the LLM processes information. It acts as that depth multiplier, which unlocks better reasoning and long context mastery.
But this clear split between what MOE does and what Engram does, it raises a really profound question for the future, doesn't it?
It does. The researchers did one last fascinating test. They suppressed the Engram module during inference, basically turned off the memory, and they found that factual knowledge tasks just collapsed. Performance dropped to about 29% of the original. A catastrophic failure.
Ouch. So the Engram is absolutely essential for remembering facts.
It is. But, and here's the kicker reading comprehension tasks, the ones that rely on dynamic reasoning, they were incredibly resilient. They retained 93% of their performance. You now have this massive, stark functional separation baked right into the architecture.
So if memory and computation are now clearly separable systems inside the model, should we even continue this expensive paradigm of trying to train new facts into a model's weights?
Yeah.
Or should future models just be pure reasoning engines that connect to these massive, easily updated, deterministic memory modules like Engram? It suggests maybe the L in LLM should stand for logic, with knowledge being a bolt-on, infinitely scalable peripheral. And that really changes the definition of what we're even trying to build.